Hi everyone, my name is Chandra Sekar. I'm from Group 6. Today we would like to present on experiment for pump configuration. Let me start with the background. The elements and design of centrifugal pumps are very important for its effectiveness. Centrifugal pumps are most frequently utilized in water or waterway system, that making it necessary to find out how they work and the way to design them. Centrifugal pumps have many benefits, that is simplicity in construction, high efficiency, ability to work against a variable head, suitable for being driven for high speed prime mover like turbines, electrical motors, internal combustion, and also continuous discharge. As you can see, this is the schematic of typical pump. Next, this is a pump performance curve. The performance of a pump is best of as characteristic curve and is comprised of the following, that is pumping head versus discharge, brake horsepower versus discharge, and efficiency versus discharge. The characteristic curves of pumps in series or parallel should be made from this data, which help engineers to choose the best pump to be used. Next, let us move to the problem statement. There are three types of pump configurations. In order to determine the best configuration to overcome the problem, that is parallel, series, single. This will include all the parameters such as pressure head, flow rate, the power consumed by the pump, and others. The relation between them is crucial in order to identify which pump is the have a highest performance. Now let's see the objective. There are three objectives on this experiment. The first is to determine pump performance with single pump, series, and parallel pump configuration. The second is to investigate the relationship between the pressure head, flow rate, power consumed, and efficiency of a pump. And the last, to compare the performance curve of different pumps. Lastly, from me about the scope, there are three scopes. The first will be understanding the mechanism of the pump in different configuration. Next, experimental study of fluid flow in the centrifugal pump. And lastly, carry out analysis of pump performance according to the parameters obtained. That's all from me. Thank you.
Assalamualaikum. My name is Mohamad Hasbullah bin Abu Bakar, and today I am going to continue present about the theory and experimental procedure. So for theory, the pump are the mechanical device placed on the pipelines network that convert mechanical energy supplied from an external force into the liquid flow from a lower potential to the higher potential. So this centrifugal pumps experiment has been set at a manual mode, making switching between series and parallel setup easier. So the volumetric flow is based on the pressure generated within the pipeline when using series parallel centrifugal pump. The volumetric flow is high while the pump pressure is low. The pump pressure is low while the volumetric flow is high. So each pump in series will have the same flow, but the total heat produced will be the sum of the pump. When they connect in series, each pump generates a head which corresponds to flow. The total head of the sum in the total head of head 1 and head 2, the heads created by the pumps in sequence at the same flow rates are referred to as head 1 and head 2. So So next we go for the apparatus. So in the apparatus we'll have pump inlet, accelerate sensor, the layout for the data acquired system and outlet. Procedure. So procedure we divided by two parts, which is first is pump, second is daisy lab. So we go for the pump first. So first conduct a thorough inspection of all apparatus to avoid any damage, since any damage or leakage at the pipe will have an impact on outcome. Second, we check that the sensor wire is connected to the DAQ as well as the flow rate meter. Then, if all checks have been completed, the apparatus are in working order, then the experiment can begin. After that, to fill the tank with water, press the green button. Next step is to keep the flow of the water into the tank under control so that the water level does not rise above the tank water level. Number 6 is make sure the pump is turned on before filling the tank with water. Number 7, turn on the suction so that water from the tank flow through pipe 1 and sensor send a signal to the DAQ to the interpreter. Number 8 is for the series pump. We will open the suction at the first and middle pumps, allowing the water to flow through the first and second pumps. Number 9 is for the parallel pumps. We will close the intermediate suction and open the first pump suction as well as the second pump suction, so that each pump will receive half of the water flow. Number 10, and then the sensor will communicate all the data or signals it receives to the DAQ to the interpreter. Number 11, we will use the flow rates meter to calculate the flow rates. Number 12, the data will be transferred from the DAQ to the daisy lab computer system. Then we go for the daisy lab. So for the daisy lab, first thing we need to connect the flow sensor to the strain gauge sensor in the NI DAQ system. Then we need to create a new NI DAQ job in the National Instrument and Automation Explorer, where we were going to use strain as the analog input sensor. Then pick analog input for acquiring signals. After that, we select the channel to connect to the national instrument. After that, in gauge factor and gauge resistance column, enter 2.11 and 1119.5 respectively. Select the continuous sample for the all equation modes. After that, click the save and run. Number 4, finally launch the daisy lab software. After that, we synchronize an instrument driver and pick analog input that was previously saved. So number 6, finally we can calibrate the sensor that need to be determined and enter the information into the software. Last but not least is 7, we make note of the reading and draw the conclusion. I think that else for me. Thank you.
This is the result for our experiment. The table shows the single pump configuration, and we use the pressure to calculate the head, which is the formula is H equals to P2 minus P1 over G, and we use the volume flow rate to calculate the water power, which is water power equals to G times head that we already calculated times volume flow rate. And this is the graph for single pump configuration. The graph correlation shows that pump head decreased as the flow rate increased. This relationship states that pump head is inversely proportional to flow rate. And this is the table for series pump configuration. We use the pressure to calculate the net head. H1 equals to P out over G, and H2 equals to P delivery 2 minus P suction 2 over G. And the H total is sum of the H1 and H2. And water power, we use the volume flow rate to calculate. Water power 1 equals to G times head 1 times volume flow rate, and water power 2 equals to G times head 2 times volume flow rate. And the water power in total is the sum of WHP1 and WHP2. And this is the graph for series pump configuration. This is the table for parallel pump configuration, and we use the pressure to calculate the net head. H1 equals to P delivery 1 over G, and H2 equals to P delivery 2 over G. And the water power formula is water power 1 equals to G times H1 times volume flow rate, and water power 2 equals to G times H2 times volume flow rate. And the water power total is the sum of the two water horsepower 1 and water horsepower 2. And this is the table for the graph for parallel pump configuration. The graph correlation shows that pump head decrease as the flow rate increase. This relationship states that pump head is inversely proportional to flow rate for parallel pump. And this is the discussion for our experiment. And for single pump, the data acquired from the DAISY lab based on these three experiments were generated. The pump's needed flow rate is determined by the height to which the fluid has to be pumped. The pattern of association between pump head and flow rate may be seen in the result. The pump head is inversely proportional to the flow rate as shown by this connection, and the power output is related to flow rate and pump head. As a result, increasing the flow rate and pump head will improve the pump's power output. And this is the discussion for series pump. Even when two similar pumps are used in pipe system, the design of a pump has a significant influence in deciding the delivered flow rate and net head to the system. The connection between series and single pump configuration is similar. When a result as the pressure head rises, the flow rate falls. The head is inversely proportional to the flow rate as shown by this connection. For parallel pump, to achieve a larger flow rate, a parallel pump design is employed. When two pumps are linked in parallel, the performance curve produced by summing their flow rates at the same head is achieved. When two pumps are connected in parallel, the head system that connects them references their suction and discharge connection to the same pressure. As a result, the total flow they create is equal to the sum of the flows generated by each pump when the differential pressure or head is the same. As for the conclusion, the results and graph from this experiment reveal a performance curve that shows as the volume flow rate increases, the net head decreases. When pump is linked in series, the volume of flow rate is roughly identical to that of a single pump, but the net head increases. When a pump is linked in parallel, the net head rises and the volume of flow rate rises with it. Thank you.